An assertion from educator Carlos Plain. In Durham School I've committed my entire calling to enabling an unequivocal speculation about the universe. Then, at that point this happens. The speculation is being watched out for. I embrace this test since it is through such looking that we advance and gain ground in science. The James Webb Space Telescope is basically disturbing some extensively held convictions in cosmology that have been seen as truth for quite some time. One more ultra-track down picture has revealed that we have committed blunders in space science. The telescope, which was wanted to uncover the focal stars of the universe, is truly risky. The previous viewpoint could introduce a completely new legitimate perspective. Not all experts are mourned about these new divulgences. Various specialists are welcoming these levels of progress since it has for a significant time frame been evident that there were issues with our previous hypothesis. The peculiarities in viewing the universe's speed of improvement alone should have brought alert for any circumstance experts an incredibly long time ago, as opposed to definitively loosening up these alarms. A large number adhered to outdated speculation. The big microwave background radiation (CMB), which is the most outdated light in the universe, was made around 380,000 years after the Big Bang, when the universe had adequately cooled for electrons and protons to approach stable hydrogen particles. This chain change, known as reionization, made the universe direct to life light. The CMB was first recognized in 1964 by American physicists Arnold Penis and Robert Wilson while they were managing New Radio Authority development. They encountered a consistent clatter coming from each direction. This disclosure was at first considered strong verification for the hypothesis of the universe's starting point. Penis and Wilson were awarded the Nobel Prize, and their revelations transformed into a critical foundation in the verifiable background of space science. The CMB undoubtedly provides a short investigation of the early universe with minute temperature changes, offering basic snippets of data about the conditions not long after the tremendous blast. Analysts used the CMB as a dependable marker to check colossal pieces of the material universe, including the universe's expansion rate. Edwin Hubble had previously made such assessments in the late 1920s. He saw that far-away enormous frameworks were making some distance from us every which way, and that their speed was associated with their relationship currently known as the Hubble guideline or the Hubble constant. Notwithstanding the reality that Hubble's assessments were not as accurate as they are today, they were critical at the point when the CMB was tracked down. Subject matter experts recalculated the expansion rate, seeing it as essentially lower than Hubble's basic examination. Subsequent recalculations using type IIA Supern NOI as standard candles gave a more definite measure. In any case, blunders remained, and the difference in expansion rate checks has been known since the 1990s. Experts have speculated that there may be issues with the CMB data analysis strategies or the possibility of general improvement. This uniqueness, known as the S8 tension or Hubble strain, suggests that how we may interpret the universe may be fundamentally flawed. Since the James Webb Space Telescope (JWST) started its tasks, it has given remarkable data that could help with figuring out the issue. Worlds so old and mature that their development may theoretically have started before the Big Bang are testing old coherent theory space science by faces what is considered to be the best crisis in present-day cosmology. The improvement speed of the universe and the speculation of how things came to be are under outrageous examination. New pictures reveal a universe that shifts from an overall perspective from past models the S8 strain has filled in as an early warning for experts who still adhere to old hypotheses, now grappling with the affirmation that how we may interpret the universe may be deficient. This weakness has left a large number of inspectors lamented and disheartened. To address this crisis, we should appreciate how science functions. Speculative specialists use a blend of mathematical models, observational data, and reasoning to arrive at conclusions. Their understanding comes from seeing peculiarities in test results and speculative examination. The term theory itself suggests advancements and considerations rather than outright real factors. Our wise data comes from pictures provided by telescopes, sound waves, and radiation captured by radio telescopes, as well as data from neutrino and gravitational wave detectors. The James Webb Space Telescope grants us to isolate the most laid-out light into person frequencies and look at it in marvelous detail. It can show what parts were accessible in vast frameworks billions of years earlier, the mass held inside them, and the number of stars present. However, Webb's photos may have limitations. For example, it can't actually perceive frameworks or dim openings that produce similar magnificence due to gravitational lensing. Our comprehension has progressed to consider different possible results as pieces of seeing much of the time. Pardoning elective explanations. New disclosures from the James Webb Telescope offer significant signs that could insight superseding old theories with new pie of information. Analysts are presently grappling with these revelations, which seem by all accounts to be so unprecedented that tracking down new clarifications is proving challenging. The latest disclosures are shaking the underpinnings of actual science, causing concern among various experts. Actual science guidelines today are still determinant, affected by Isaac Newton's 17th-century work for a seriously long time. His guidelines of development and gravity have provided the foundation for understanding the real world and the universe. Newton's guidelines function commendably under typical conditions on Earth. In any case, in space, his considerations expected expansion to an incredible degree, accomplished by Albert Einstein during the 20th century. Einstein's special theory of relativity, published in 1905, changed how we could decipher reality, showing that the laws of actual science are similar to the spectator's movement. His general theory of relativity, published in 1915, expanded these considerations with mathematical figures of general relativity, gravitational idiosyncrasies, considering the bend of spacetime achieved by masses like stars or universes. While Einstein's theories were clear in various regions, he saw their limits and searched for a binding, unifying structure. Without progress, no scientist has yet succeeded in this attempt. It is fascinating to consider where the mistakes could lie. Mayo Kaku, a prominent American astrophysicist, proposed that solving this issue could lead to a Nobel Prize. We truly need to explore what reality might have been, confused whether there have been misinterpretations of idiosyncrasies, or if telescopes themselves might be to blame. Dark matter and dark energy are top suspects in the cosmological crisis. Current models suggest that dark matter and dark energy together account for around 95% of the universe. Neither has been clearly seen or demonstrated to exist. They may not exist by any means, or perhaps have properties we don't yet understand. One chance being inspected is that dark matter's properties might have evolved over time, potentially showing some kind of insight into gravity which should cause an interaction through mass or spacetime. Gravity has not been definitively shown to act exactly as expected. In any case, the reality of spacetime twist, as proposed by Einstein, has been supported several times. We can't completely block the credibility that gravity has astonishing properties, or that some other effect is causing gravitational interaction over time. Explicit properties in cosmology and space science have been spread out as central constants recognized as reliable, generally due to their consistency. Assessments suggested that small assortments in these constants could offer new pieces of information into the universe, potentially grasping idiosyncrasies without dark energy. It is also possible that our understandings of light movements have been off, leading to mistaken distance assessments and grandiose framework ages. Perhaps our assumptions about the universe's conditions were imperfect, or we misread the cosmic microwave background radiation. It could attempt to be simply that the universe doesn't originate from a singular early stage, testing the speculation of the Big Bang. Little bungles in the Webb telescope or other observational devices can't be ruled out. Some subject matter experts and scientists recognize that mistakes in instrumentation, data handling, or understanding are generally possible. The persistent reassessment of cosmological hypotheses highlights the principal nature of legitimate advancement, the ability to change and move our understanding based on new evidence. The James Webb Space Telescope's observations are more than an innovative leap. They represent an enormous moment in our journey to unravel the universe's insider secrets. As we wrestle with these revelations, it is key to see the broader context and repercussions of such reliable changes in the area of cosmology. The methodology involved is often driven by the need to refine hypotheses in alignment with new insights. The discovery of exceptional anomalies or abnormalities in established hypotheses can be unsettling. However, it also presents a critical opportunity for legitimate development. Hypothetical models in cosmology are made to provide a clear structure for understanding the universe's origins, progression, and advancement. However, as new data emerges, these models should be tested and, if necessary, rethought to accommodate new insights. One critical area of focus is the nature of dark matter and dark energy, which are central to contemporary cosmological models. Dark matter, a subtle type of matter that doesn't emit or absorb light, was proposed to account for irregularities between observed galaxy rotations and the mass expected by recognizable matter. A lone dark energy was introduced to address the observed accelerated expansion of the universe at any rate. Despite their fundamental positions in current models, both dark matter and dark energy remain intriguing, with investigations on Earth having until now failed to indisputably identify them. This has led researchers to explore alternative hypotheses and possible explanations. The trial of grasping dark matter and dark energy is heightened by the vast scale associated with cosmological studies and the observation of universes. The cosmic microwave background radiation, along with other remarkable features, provides indirect evidence of these components, yet their elusive nature remains subtle. This uncertainty has prompted analysts to consider a range of hypotheses, from modifications to existing models to entirely new laws of physics. Some theories suggest that dark matter could be made of more intriguing particles than previously thought, or that dark energy could represent a new fundamental force. Another captivating area of cosmological study is the investigation of cosmic inflation. This theory proposes that the universe underwent rapid expansion in its earliest moments, leading to the vast-scale structure we observe today. While inflationary theory has successfully explained various features of the universe like its homogeneity and flatness, it also raises questions about the nature of the inflationary period itself observations that challenge established models of inflation could lead to revisions in how we interpret the universe's early history. Finally, the search for extraterrestrial life remains a principal driving force in space exploration. The discovery of exoplanets, planets orbiting stars outside our solar system, has opened new avenues for studying the conditions necessary for life. Advances in telescope development, for example the James Webb Space Telescope, enable us to explore the conditions of these exoplanets for potential biomarkers. The possibility of finding life beyond Earth holds profound implications for how we might interpret the universe and our place within it. In conclusion, the reassessment of cosmological theories is a testament to the strength of the scientific method. The James Webb Space Telescope and other advanced instruments have provided astonishing insights into the universe, prompting researchers to revisit and refine old theories. This process of continuous inquiry and correction is vital for advancing our understanding of the universe and addressing the fundamental questions that lie at the core of cosmology and space science. As we continue to explore the universe, we remain engaged in a quest for knowledge that not only seeks to answer key questions but also inspires future generations to push the boundaries of human comprehension.